The Express Python interface allows for the creation of variables and linear or nonlinear constraints in the form of NP arrays. In these code snippet example, the NumPy library is used to create two NumPy arrays of variables and a set of constraints in an efficient way. Note that the D-type must be defined as xp.npvar when using the problem.addVariable function. To create NumPy arrays with one or more dimensions in a more compact and readable manner, use the method problem.addVariables with one or more integer arguments to automatically create a NumPy array for all combinations of the corresponding zero-index sets passed. Additional arguments, such as variable names or bounds, will apply to all elements of the array. The broadcasting features of NumPy arrays allow the replication of operations on each element of the array, for any number of dimensions, promoting a more compact and efficient modeling. In this example, a set of constraints for a set S is created in a compact form by using NumPy arrays of variables. In a second example, the broadcasting features are leveraged for creating and adding a quadratic constraint containing two three-dimensional arrays of variables. When performing dot operations on vectors, matrices, and tensors in arrays with express variables, use the express dot operator, which is functionally equivalent to the dot operation, but allows performing the operation in NumPy arrays containing an unlimited number of express variables. When using multidimensional arrays of variables, keep in mind that the last dimension of the first array must match the size of the penultimate dimension of the second vector, just like in the second example shown, where 8 new constraints are created by using the xp dot operator. The Jupyter Notebook example called NumPy arrays demonstrates the basic use of NumPy arrays and the xp dot operator for increasing model building efficiency. In this example, two matrices with different shapes are defined before the problem creation. Then, a set of 5 decision variables are added to the problem. Note that by using problem.addVariables with an integer argument, a NumPy array of variables is created. In the next code cell, the express dot operator is leveraged to create 6 linear constraints from the dot product between the matrix A and vector of variables x. Note that the right-hand side values of the resulting constraints are passed in the form of a NumPy array that is mapped to the constraint expressions that originated from the dot product. The second object defines a convex quadratic constraint obtained by the dot product between the vector x and the matrix Q in a simplified and compact way. The last code cell of the notebook sets a convex quadratic objective function by using the dot product on variables x minus a randomly generated vector. Then, the problem is optimized and exported to a file with LP format. The resulting LP file, named numpy.lp, can be opened with an editor to validate that it contains the 7 previously defined constraints.